want to take a look at how we get our energy from nuclear processes. And typically we do that by using fission. And so I'm showing a reaction here of uranium-235, which has 92 protons. And when you hit uranium-235 with a neutron, it can split up into any number of possible different products, but one of the sets of possible products is the production of strontium-90, xenon-144, and two other neutrons. And then, of course, you also get energy out of this because when you add up all of the masses here, we typically lose about 2/10 of a gram from this particular reaction. And of course, if you lose 2/10 of a gram for every uranium atom, you're converting that mass into energy. Remember, E equals mc squared, and so you get a boatload of energy out of this particular reaction. And you can imagine if you had a mole of uranium, how much energy you would get from that. Recognize, however, though, that you are producing two more neutrons. And so if you have only one uranium-235 atom here, then that's kind of the end of it, and all those two extra neutrons just kind of go floating out into space. But imagine if you had quite a number of uranium atoms around. Now those two new neutrons that you have formed can go in and react with more uranium-235, and you will get two more reactions going. And that's going to produce four neutrons, and those four neutrons can go and react with four more uranium-235s and create eight more, and you get what is referred to as a chain reaction. And a chain reaction is what you would get if you were to have an explosion go on. So that's not what we want to do. In order for that chain reaction to occur, you have to have a critical mass of uranium-235. The critical mass is the amount of material that's necessary for a chain reaction to occur. Now, typically, when we look at harvesting uranium from the Earth's uranium is mostly uranium-238. About 99.3% is uranium-238, and only about 0.7% is uranium-235. So we end up purifying the uranium-235 from here so that we can enrich that uranium-235 to about 5% to uranium-235, which is what we call fissionable, and about 95% uranium-238, which is non-fissionable. We convert that uranium-235 into a small uranium dioxide pellet. That pellet is about an inch long or so, and about the diameter or so of a pencil, maybe a bit bigger than that. This single pellet containing 5% uranium-235 contains as much energy as a ton of coal or 150 gallons of oil. So you get a feel for just how much energy one can get from a single small pellet of uranium that's been partially enriched. This diagram is a diagram of a nuclear power plant. And so the idea here is in red in the reactor right here, you can see where the fuel exists, and those exist in rods. And then there are some control rods that sit above that. And so when you want the reaction to move forward, you pull the control rods out, and then you don't have a critical mass of the uranium there, but you can allow these neutrons that are being formed to go and hit other uranium particles that are in another rod. And if the reaction is going too fast, then you can drop the control rods, and those control rods contain something, maybe beryllium or something of the sort, that can pick up these neutrons without creating another radioactive process. And so the control rods are there to temper how quickly this reaction is going to go. The faster you want it to go, the more it's going to heat up the liquid that's in that reactor. That liquid then gets pumped around. As you can see, it heads up to the steam generator, and in the steam generator, that cold liquid there gets heated up and converted into steam. That's generally just water, and the steam then goes in and it can turn the turbine. As the turbine turns, it creates electricity in the generator, and then that can pump the electricity out into the switchyard. The hot liquid that gets condensed from the steam is going to have to be cooled down a little bit, and so we send cooling water from the reservoir and the cooling towers into that liquid, and that liquid then gets pumped back into the steam generator, which can then be heated up again, and so on and so forth. So that's the idea behind how a nuclear power plant is going to work.